All right, so essentially what I forgot to put in the slide, but essentially what we finish off with yesterday, we were trying to make an amide from a carboxylic acid, okay? And so what this reaction was, let's say we have a carboxylic acid like this. We're trying to react it with an amine to make an amide. All right, and we said that the first thing that happens, in fact, is not the attack of the amine at the carbonyl carbon, but we just get an acid-base reaction. Okay, and so this generates this carboxylate plus the ammonium ion, like this. All right, we did say that if we just heat this thing over 100 degrees, we can, in fact, sometimes derive this to the amide. But it's not really a very good reaction. Okay, so what we talked about is that a strategy that we might be able to take is to convert this OH of the carboxylic acid into a better leaving group. Okay? So what's a better leaving group that we could put on there? Well, the first thing might be all right, so essentially what I forgot to put in the slide, but essentially what we finish off with yesterday, we were trying to make an amide from a carboxylic acid. Okay, and so what this reaction was, let's say we have a carboxylic acid like this. We're trying to react it with an amine to make an amide. All right, and we said that the first thing that happens, in fact, is not the attack of the amine at the carbonyl carbon, but we just get an acid-base reaction. Okay, and so this generates this carboxylate plus the ammonium ion, like this. All right, we did say that if we just heat this thing over 100 degrees, we can, in fact, sometimes derive this to the amide. But it's not really a very good reaction. Okay, so what we talked about is that a strategy that we might be able to take is to convert this OH of the carboxylic acid into a better leaving group. Okay? So what's a better leaving group that we could put on there? Well, the first thing might be chloride if we could. Okay, so that would essentially go back up to the top of our reactivity list, and we could then go down. Okay, so to convert a carboxylic acid to an acid chloride is kind of making the OH into a better leaving group in two ways. First, we're going to make the carboxylic acid into a better leaving group in the process of making the acid chloride, and then, of course, the chloride is a better leaving group than the carboxylic acid anyway. Okay, so we're going to use this reagent. This is called thionyl chloride. You guys remember this from before, from last semester? Did you talk about thionyl chloride? No? Yeah? What did it do? Yeah?
Couldn't it replace a hydroxy group with alkyl to a carbocation reagent? So
Well, so it was a way to convert an alcohol to a alkyl chloride. Okay? So in essence, you know, one of the ways to do substitution reactions on alcohols is to make the OH into a better leaving group. You can either protonate it to make a water molecule, make it come off, or thionyl chloride reacts with the OH to make a better leaving group, and then chloride comes in and does a substitution. And so we're going to essentially do the same thing here. So let's just draw out our main product. It's going to be the acid chloride. All right, so let's just take a look at how this works so we can understand why we can drive this less reactive reactant to a more reactive product. Right, so we're going uphill in energy. Okay, so the way that this works is well, we could draw this either way. Should we do it that way? No, let's do it, I think, the other way around. Because we already said that it's the carbonyl oxygen, which is the more basic site, right? If we're going to protonate an acid, that's where we're protonating. And so really, if we're going to do a reaction with the carboxylic acid as a nucleophile, then it really should be that oxygen. Okay? So this is going to go like this. And this is just going to displace the chloride. All right? If you want here, let me redraw that. I'm going to do it in a slightly different way, just to streamline this. I'm going to use the pi bond like this, and then I'm going to push these electrons down like that. Okay, so this is going to give us, let's figure out what we're going to actually get. This oxygen is now going to be attached to the sulfur, and the sulfur has one chlorine left on it. Okay, the other oxygen is now going to be protonated like this. Okay, so in the second step, we're going to make this neutral, and so we're just going to use chloride to deprotonate this position. And notice we essentially have, looks kind of like a carboxylic acid tipped on its side, but we've made this whole group equals a very good leaving group. Okay, so that whole thing is going to come off. All right, so now this can react with another chloride. And if we want to be complete about this, we come into here. We're going to go to a tetrahedral intermediate. O minus, O sulfur. And here's our chloride. Now, chloride is a good leaving group. If chloride comes off as a leaving group, then we just go backwards. Okay? However, this sulfur group up there, in fact, ends up being a very good leaving group. And let me show you how this works. So this is going to come down to reform our carbonyl. The carbon-oxygen bond is going to go all the way up here and make a carbon-sulfur double bond. And chloride is going to come off. Okay, and so we're going to go back this way. We get our acid chloride, plus we get SO2 plus chloride. All right, so if we're balancing it, one of this chloride kind of cancels out with one of these ones that we use down here. Okay, so the reason why this goes so well to products is that SO2 is actually a gas. All right, and so as the reaction runs, SO2 is produced and it just bubbles out of the solution. And so it's like removing one of the products. So Le Chatelier's principle says as you remove this product, it's just going to keep driving the reaction toward the products. Okay, and so that's why this reaction can continue all the way to products, even though it's kind of going up in energy, because there's no way for it to go backwards. Okay, it becomes irreversible because the SO2 is gone. All right, so then once we've made that acid chloride, of course, we can make any of the other carboxylic acid derivatives from there. All right, so this is one way to do this. The other way, some reagent that we could call a coupling reagent. Okay, and they use these a lot to make like amide bonds when they're making peptides, so linking amino acids together. One example is this compound here. I had to shrink it down to fit it in because it was too big. This is called, we just can refer to it as DCC. It stands for dicyclohexyl carbodiimide. Okay, and it just acts as a coupling reagent. So, and in the end, what it's really doing is, like I mentioned, the strategy is going to make that OH into a better leaving group. Okay, so let's look at how this one takes place. So one of the nitrogens on the DCC acts as a base in the first step. So it reacts with the acidic compound in the reaction, which is the carboxylic acid. So we get the carboxylate plus, let's see how I want to draw this. This thing is too big. Here I'm going to draw that H over there. Carbon. Like this. So what about that center carbon there? Okay, let's see. Can I get my pointer? This one right here. Right, what's the hybridization of that carbon in the middle? SP. Right, because it has two pi bonds. One pi bond going one direction, one pi bond going the other direction. Okay? So the p orbitals that make those pi bonds, remember we make pi bonds by two p orbitals bonding side to side. So how do you think the pi bond that goes in towards one nitrogen is oriented relative to the pi bond going in the other direction? Now they're going to be at 90-degree angles, right? So the pi bond going to one nitrogen is going to be going this way. The center carbon has another p orbital that's 90 degrees away, and that's going to go with the other pi bond on the other nitrogen. Okay? All right, so this nitrogen now has a plus. Okay, so what can happen now is that this carbon can act as a nucleophile and attack that carbon right there. So this is kind of like if we just covered up one half, it's kind of like an imine, right? A protonated imine. So these electrons go back to the nitrogen because that has the plus charge. I'm going to loop way down here to make sure we got enough room. Okay, so this goes to the middle carbon. This, let's see, is still a double bond there to this nitrogen. Like this. right? No other charges or anything on here because we had a minus and a plus that came together. All right, so now what we're going to have is that this whole group right here is going to essentially function as a leaving group. Okay, so we can react this with our nucleophile, which is the amine. And I'm going to loop this all the way over here. It's going to attack here. We're going to have to draw another tetrahedral intermediate if we can fit it all in here. I'm going to loop this down this way. And, oh, we added, oh man, I'm going to have to draw this all again too. Like this with a plus. Okay, I'm going to, okay, we've got to do one more. We just have to deprotonate the nitrogen so it doesn't come back off as the leaving group. And then we can do the big, let's see, we're going to use, what should we use as the base in this reaction? Probably the amine. Okay, so our base is going to come down and pull this proton off. And we got to draw one more of these, dang. And this was the oxygen. So we could have just put R groups or something on there. There are other related coupling reagents that instead of the cyclohexyl groups, they have isopropyls or different kinds of groups like that. All right. So now the important part, the thing that's going to happen here is I'm going to kind of do this in one step. I'm going to cheat a little bit. But this is going to come down. We want to reform our carbonyl because we're trying to make an amide. This group is going to come off, and this double bond is going to go form a carbonyl over there. And this double bond, I'm just going to show it coming up to react with a proton. Right? That one, in likelihood, probably gets protonated first. Okay, but I don't have room to draw it in. Okay, so let's see what we got out of this. Okay, so we ended up breaking this bond right here and reforming our carbonyl. So I'm going to have to squeeze this in here. We got, oops, we got our amide, right? And what did that other huge thing give us? Okay, so I'm just going to reorient it. We've got a carbonyl in the middle, an NH on this side with a cyclohexyl group, and NH on this side with a cyclohexyl group, like that. Okay, so let's think about, so really, usually what we do is we lose the OH and an H, so we've lost a water molecule in the process, right? So to balance this whole thing, we should get our amide plus a water molecule. So where did the water molecule go? It's like one of those drawings, right, that has all of the little shapes and, oh, there's a baseball mitt hidden in the tree or something like that. Okay, so the water molecule is going to include this oxygen, right? And these two hydrogens right here. Okay, so that's where the water molecule went. So this dicyclohexyl carbodiimide turned into this other functional group, which looks like kind of like a diamide. This is actually called a urea. So actual urea itself is a molecule just like this. Two. Right, so that functional group is called a urea. Okay, so what we've done in a lot of complicated steps here is we've used this coupling reagent to make a better leaving group and essentially kind of pull a water molecule off of that carboxylic acid. You just couldn't have lived without that, right? Yeah.
So, on an exam, how would we...
Let's just say that on an exam, you won't find this mechanism. Because I wouldn't want to grade it. All right, so the point is, here though, if we look at this, well, if you could actually follow it now, it's just this. I wish my picture gave me all that extra space over there. So, but if we think about it, if we look at the individual steps, then, we can, I think, fit this into what we've already learned, right? So in essence, if we look at this carbodiimide, we have these carbon-nitrogen double bonds. So if we want to increase the electrophilicity of this central carbon, then if we protonate on the nitrogen, it makes that a better electrophile. So first we protonate there. The carboxylate's a nucleophile. Okay? So this kind of reaction right here is exactly, if this was water, it would be exactly how it would hydrolyze an imine. Okay? Once we've done that, this is a nucleophilic attack just like on a carbonyl. Right? If we protonate a ester or something, the oxygen has a plus, we attack at the carbonyl carbon. Okay, so we get this product, and then this reaction, this is just attacking at the carbonyl, the tetrahedral intermediates, we got acid-base chemistry, all of this, it looks much more complicated than it is because this leaving group is just so big, right? It just makes it look complicated, right? If maybe this was an anhydride, then we could do this, or, but each individual step are types of reaction steps that we've seen before. Okay? In my opinion. Okay, so here's kind of a summary of all of the carboxylic acid derivative chemistry that we have looked at and what you can turn into what. Okay, so like we talked about, the acid chloride is the most reactive. Okay, so if we look across the list, right, we can't turn it into a carboxylic acid. This is just itself, right, unity or whatever. We can turn that acid chloride into everything else. Okay, we go to the anhydride. We can turn it into everything that is less reactive than it is. We can't go back up to the acid chloride, though. Okay, we can only go downhill. If we go down to the ester, then again, we can't make an acid chloride or an anhydride, but we could make a carboxylic acid. We can make another ester, okay, because we added in the transesterification, and we can make an amide, because those are either going equal in energy or downhill in energy. And if they're equal in energy, then we can use Le Chatelier's principle to drive it in the direction that we want to. When we got down to amides, then we really can't make very many of these, and we could only make the carboxylic acid, which is actually slightly up in hill in energy, but if we add so much water into it, we can kind of drive the reaction in that direction. Okay, the one place that's unusual a little bit is the carboxylic acid, because we can make, from the carboxylic acid, we can make the acid chloride. All right, it says you can make the anhydride, but that's not such a practical reaction either. They show making a cyclic anhydride, but that's not really so useful. So let's just forget about that one. Mostly, except for making the acid chloride, the other ones are all going downhill in energy. Okay? So the easiest are going from the top down. Okay? And if we get down low, then we can always make a carboxylic acid, and we can convert that to an acid chloride and go back up to the top if we need to go upwards. All right? And it's not kind of superficially obvious that it is a carboxylic acid derivative, right? And is the nitriles. Okay, so nitriles have this carbon-nitrogen triple bond. If they are an anion, like this has a non-bonding pair over here, we call it cyanide. Okay, sometimes if you were naming something complicated and if there was something else that had a higher priority, you might call it a cyano group. Okay? So we know one way, not really to make the nitrile, but to add it to an organic molecule. Okay? And that just involves using an alkyl halide and using cyanide as a nucleophile. Okay, so this typically just does SN2 substitutions. And we've incorporated this nitrile into our molecule. Okay, in fact, this works if we could have methyl halides, I'll put an X, methyl halides. We could have primary alkyl halides, and we can even use this with secondary alkyl halides, and these are typically all SN2 substitutions because cyanide is a good nucleophile, but it's not that strong of a base. Okay, so it'll usually do SN2 substitutions with secondary alkyl halides instead of doing elimination reactions. Okay? All right, so what's more important than just adding it on is what we can do to it once it's on there. All right? The first thing is that we can do, and this is what really shows that it's a carboxylic acid derivative, is that we can do a hydration reaction. And so this can be done in acid. You can also use hydroxide and do it in base. But what you get out of this is a carboxylic acid plus the nitrogen would come off, and if we're an acid, it would be in its acidic form, so it would be the ammonium ion. All right, so let's just take a look at how this one would happen. Just because we're on a roll with these big mechanisms, we're getting so good at them, right? Okay, so the first step, to make the nitrile carbon there be more electrophilic, we're going to protonate on the nitrogen. And we're not going to really do this whole mechanism, but we're going to turn it into something we already know how to deal with. Okay, so we protonate there. And now that, because we could draw a resonance form that looks like this. Okay, we just move one of the pi bonds up onto the nitrogen. So this is increasing the delta plus on that carbon. So then water can act as a nucleophile. Comes into the carbon there, and these electrons go up onto the nitrogen. And so what we're getting here is now we have a nitrogen carbon double bond and our water molecule attached. Okay? So, usually in all of these steps, we get an intermediate that has a charge, we need to make the neutral one, intermediate. Okay, so we're just going to use the water, another water. Going to remove this. Oops. This to be blue. And we get to this intermediate right here. Okay, so this intermediate has an isomer. Okay, and we're going to draw this. So it's not resonance. This is actually isomer, and I'm not going to show how this takes place because we don't want to draw out that many steps here. But you can tell me what type of isomer this is. Like this. Okay, so how are those two compounds related to one another? They are constitutional isomers, but they're a special kind. They're tautomers. Okay, remember when we had enols and ketones and stuff? So in this isomerization, notice that the proton on the oxygen gets transferred onto the nitrogen, right? And then the double bond shifts. Okay, so these are tautomers. Okay, and look at what kind of a functional group we've generated, right? So what have we made? An amide, right? So we've added one molecule of water, and we've converted the nitrile into an amide, okay? And then it's just going to continue. We've already looked at the hydrolysis of amides, right? So we just continue on, and we're not going to go through all of that. Okay, so this part is just amide hydrolysis. Okay, so again, it would protonate on the carbonyl oxygen. Another water molecule would attack. Right, we'd have some acid-base chemistry. We'd need to protonate the nitrogen again to make it a good leaving group. And we'd go to the carboxylic acid. Okay, so in essence, the first process that we do is we add the one water molecule to convert the nitrile to the amide, and then the amide gets hydrolyzed. Okay, so we're trying to take it from something new into something we've seen before. Let's go back. Well, the significance of the two water molecules is that it takes two, right? Because one water molecule is right here, right? And that converts the nitrile into the amide. And then we have to hydrolyze the amide, so that takes another water molecule to cleave the carbon-nitrogen bond. Okay? Basically, it's because we have two pi bonds in the nitrile. We have to do the reaction twice. Okay. Ooh, what just happened? Oh, it jumped to the next slide. I didn't even do anything. Ooh. Spooky. Actions, we can reduce nitriles. If we reduce them with a very strong hydride reducing agent, right, like lithium aluminum hydride, it will reduce the nitrile all the way to an amine. So we add 2 hydrogens here and 2 protons onto the nitrogen. Okay? What else can we reduce with lithium aluminum hydride to get to a primary amine or to an amine? An amide, right? So we could also get to this same molecule by reducing this amide, right, with lithium aluminum hydride followed by water. Okay, those would both go to the same thing. If we use a weaker hydride reducing agent, remember dibal, which is diisobutyl, use isobutyl aluminum hydride. Okay? And it converts a nitrile into an aldehyde. Okay. So let's take a quick look at how that would take place, just so we can see how these are related. Right? So first step is the hydride attacks the carbon of the nitrile. Okay, we already had 1 non-bonding pair of electrons on the nitrogen, so now we have 2, and then nitrogen has a minus charge. And we've added a hydrogen there. Okay, so essentially it's just going to stop here with the dibal. It's not going to reduce any further. It's just going to stop. And so then what we have to do is we have to quench the reaction. And I think we're going to use, instead of water, I'm going to add a little bit of acid into this as well. So weak acid. And so we're going to add water and acid. The first thing that's going to happen is we're just going to protonate the nitrogen because it had a minus charge on it. Okay, and then what functional group have we made here? An imine. Okay, so this is an imine. And when we hydrolyze an imine, we're using water and acid. Then remember, we cleave off the carbon-nitrogen double bond and we make an aldehyde if there's an H on the imine. Okay, so this is just imine hydrolysis. Okay, I know went over the mechanism of the imine formation, and the hydrolysis is just a reverse reaction of that. You fit one more in, right? And then we'll be done with all of our reactions for this exam. Okay, so I think this is a kind of a cool one too. In fact, our other old textbook didn't even include this, so you guys got a bonus reaction here. All right, plus, let's add some acid in with this one too. So it would give us a ketone and the ammonium ion. So the nitrogen comes off as the ammonium ion. Okay, so this is going to work just like that last one, really. We have the Grignard, though, this time. Instead of a hydride, tacks the carbon of the nitrile, goes to this nitrogen like this. We've just added this propyl group. This has a minus charge. This is a benzene ring. And so it stops here. Okay, it won't add again. And so then we add the aqueous acid, H plus, and water. We quench the reaction and we hydrolyze this imine. Okay, so this is also an imine. This is an imine of a ketone instead of an aldehyde. And then this hydrolyzes. So this is imine hydrolysis as well. Okay, so we could, think of like something like this. We could start with an alkyl halide. We could do a substitution. Maybe I should do this in the reactions tomorrow. And then from there, we could even add another Grignard. 1, 2, H plus, and what do we get? We get this ketone. Okay, so think about, I'll weave this in to something tomorrow, how we could do this in another way. This allows us to do, we have other ways to do this as well. All right, so I will see you guys in the morning. Go to the review session tonight.